So this first lesson is increasing and decreasing and stationary points. Remember, when you differentiate things, you are finding the gradient. So we're going to talk a bit about gradient here. The gradient of a straight line, we know, is the slope. If something is in y equals mx plus b form, it's the number that's in front of the x. We calculate a gradient using rise over run for straight lines. You've been learning that for many years. There are 4 different types of gradients. There is the uphill gradient, which is the positive gradient. There is the downhill gradient, which is negative. There is the vertical gradient, which is undefined. The reason that is undefined, because if you think of rise over run, there is no run, there's no horizontal component, which means the run is 0, and we can't divide by 0, hence undefined. And a horizontal line is a gradient of 0. Okay, so straight lines, that's pretty straightforward. But we're going to be looking at curves. To find the gradient of a curve, it says here, when finding the gradient of a straight line in the number plane, we think of the change in the y values as the x changes. This describes the rate of change. However, in most examples in real life, the rate of change will vary. For example, a car would speed up and slow down depending on where it is in relation to other cars, the traffic signals, and the changing speed limits. So for curves, if we are trying to find where a gradient is increasing, that means where the gradient is positive or greater than 0. So remember our notation: if we have a function f of x, when I differentiate it, it becomes f dash x. And when that is greater than 0, meaning positive, my gradient is increasing. Curve is going up. If I differentiate and it is less than 0, that means it's going down, which is decreasing. This is a very exciting one here, though. If we differentiate and it is equal to 0, then we have found a stationary point. Also, we have a word here that you'll want to know, the word monotonic. A curve is monotonic increasing or decreasing if it is always increasing or always decreasing. So that means that for monotonic increasing, the gradient is always greater than 0. Everywhere where the curve exists, it is always a positive gradient. If the gradient is negative absolutely everywhere, that is monotonic decreasing. Okay, next part. We have a very interesting curve over here with lots of points on it. We want to identify for the curve where it is increasing, decreasing, and stationary. So that's over there on the right-hand side. So increasing is anywhere where we have the curve going uphill, a positive gradient. So for example, here at A, if you were to draw a tangent going through A, that is sloping uphill. So A is increasing. Is there any others? G. Very good. G over here is also sloping uphill. So A and G are both at increasing points. Decreasing means going downhill. So here is one at C. We're going down, downward slope there. So C would be the first one. Is there any others? E, correct. And I, correct. So let's have a look at the stationary ones, which is where the curve will flatten out to a 0 gradient. So the obvious one here is at F. That's an obvious turning point. Gradient is 0. There's another one here at H. There's another one here at B. D. And there is one that's a little bit sneaky, which is at D. Okay, so D, you can see that this curve actually flattens out to a 0 gradient before it starts decreasing again. So when we talk about turning points, B, F, and H are turning points where it completely changes direction. But D is a stationary point that we call a point of inflection, where we're going to talk about concavity more later, but the concavity changes. It comes down to a zero gradient, but it doesn't completely turn around and go back the other way. Okay, so all of those points were B, D, F, and H are all stationary points. Okay, next page. Describe the gradient of each of the following curves. So the important things to recognize are the turning points. So for A here, this turning point, the gradient would be 0. On the left-hand side of that turning point, the curve is increasing, so they are positive gradients. On the right-hand side, the curve is decreasing, so they are negative gradients. If I were to write down a description in words, I would say it is increasing to a maximum stationary point and then decreasing. So I'll write that down for you. Let me make that bigger. SP is short for stationary point. So increasing to a maximum stationary point, then it is decreasing. If we look at part B, start with the zeros. So there's a turning point there, there is a turning point there. 2 zero gradients. Starting from the left side of that curve, we're going downhill, so we're decreasing, negative gradients down here. We get to the stationary point, the curve turns around, and now we're going uphill or positive gradients to the next one. Curve turns around again and negative gradients. Okay, so to write a description, I'm going to say it is decreasing to a minimum stationary point, then increasing to a maximum stationary point, then decreasing again. This gets a bit wordy, doesn't it? All right, so decreasing to minimum stationary point, then increasing to maximum stationary point, then decreasing. And the last one, the more bends it has, the more things there are to describe. Okay, so find all those zeros. There's a zero, a maximum up here, minimum, and then another maximum. So it is a positive gradient to the maximum, negative gradient to the minimum, positive gradient to the next maximum, and then negative gradient for the rest. Okay, so let's put that into words. Increasing to max stationary point, decreasing to minimum stationary point, increasing again to maximum stationary point, and then finally finishes by decreasing. It is unlikely that you're going to have to write out a wordy explanation like that, but it is good to get you thinking about those changes in slopes and that the stationary points are what is dividing it up. Okay, so question 2. Find all x values for which the curve f of x is equal to x squared minus 6x plus 1 is increasing. So, increasing, there was a definition on the last page, was that the derivative had to be greater than 0. So all of the differentiation techniques that you learned in year 11 could come up at any time. Most of the time it will be the straightforward one, but remember things like function of a function, product rule, quotient rule, all of those kind of things could come in as well. So here's a little bit of practice. If I have f of x equals x squared minus 6x plus 1, if I want to differentiate that, this is no tricks involved in this one, it's just a normal looking parabola, quadratic there. The power comes down and multiplies with the number at the front. So the 2, there is a number at the front, so I just bring the 2 down. The x stays there as the base, and you subtract 1 from the power. So that would become an x to the power of 1, but we don't need to write the 1. Moving on to the second term, I have a negative 6x. So there is no, the power is a 1. So when I bring that down, it's still a negative 6 at the front. The x would then become a power of 0, but anything to the power of 0 is just equal to 1, which basically means the x disappears. Any constant numbers, the 1 on the end, for example, does absolutely nothing for the gradient. Constants always disappear when you differentiate. Okay? All right, so my derivative is 2x minus 6. I am now wanting to find when my derivative is greater than 0, because greater than 0 means increasing. So my derivative was 2x minus 6. It has to be greater than 0, and I can solve that for x. So move the 6 across to the other side. 2x is greater than 6. Divide by 2. X is greater than 3. So for any value greater than 3, that parabola is going to be increasing. So 3 is probably where the turning point is, and anything to the right of that is going to be increasing. All right, next one. Question 3, find the points on the curve y equals x squared minus 3x minus 10, where it is stationary, increasing and decreasing, and then sketch the curve. So I'm going to have to differentiate so that I can see what's happening with the gradient. So let's practice that again. This time, because it's a y equals equation, you can either use dy over dx for the gradient, which is the long version that most people try to avoid, but it does actually get used in some questions sometimes, so you need to be aware of it, that that means gradient. But the shorter version is to write down a y with a little dash. Differentiating the x squared. The 2 will come down to the front, x, and subtract 1 from the power means power of 1. Differentiating the negative 3x will be negative 3, the x will disappear, and the negative 10 constant will disappear. All right, we have our gradient. To find a stationary point, okay, because that is key to where it changes from being increasing to decreasing, right? So the stationary point is going to be when the gradient is equal to 0. So I'm going to solve that. That's 2x minus 3 is my gradient. I'm making that equal 0, and I'm solving it for x. So 2x equals 3, divide by 2, x is equal to 3 over 2, or 1.5. Because the question asks me to find points, it's not enough to just find the x value for this. I need to also find the y value. So once you found that point, sub it back into the original equation for y. Do not sub it into the gradient equation. Common thing, I'm trying to emphasize that. Some people just go, yep, let's just sub it back in and I'm putting it back in. No, not here. That's the gradient. I'm not trying to find the gradient at 1.5. I already know the gradient is 0. I'll just get 0 again. I want to find this as a point on my curve, which means I have to sub that 1.5 back into my original equation for y equals. Okay, so y equals 1.5 squared minus 3 times 1.5 minus 10. And has anyone done it? Cool. So I have got a stationary point at 1.5 was the x value, and minus 12.25 for the y value. Remember, we also want to find where the curve is increasing and decreasing. This curve, looking up here at the original equation, is a parabola. It is a positive x squared, which means it is a concave up parabola. So if this is my turning point, anything to the left of that 1.5 is going to be, careful, decreasing, because it's going to this. If my turning point, I'll draw it over here so you can see it. 1.5. I'm going to put it there, not to scale. If this is 1.5, negative 12.25, and I know this is a concave up parabola, anything to the left of this point is coming down. It is decreasing. Okay, so I'm going to say decreasing, whoops, decreasing when x is less than 1.5. And then when I go to the other side, it's going to be increasing. So increasing when x is greater than 1.5. So I've already got most of my sketch there. I put the turning point on there. I'm not really asked to find x-intercepts. I could include the -10 on there for the y-intercept because that's easy to read off my equation. That's enough of a sketch. You just want to be able to show where the turning point is and actually see the decreasing, turning point, increasing. Question 4. Find any stationary points on the curve. So stationary points are found by differentiating and making the gradient 0. This time we have a power of 5 for our graph that we're differentiating here. So remember our notation, y dash for the derivative. To differentiate x to the power of 5, we bring the 5 down the front, keep the x, subtract 1 from the power, so it becomes a power of 4. For the second term, I have minus 80x, so it'll be minus 80, and the x will disappear, constant disappears. Okay, stationary points are going to be when my derivative is equal to 0. So that is 5x to the power of 4 minus 80 is equal to 0. I want to get the x by itself. So let's move the 80 across. 5x to the 4 equals 80. Divide by 5 equals 16. And when I, here it is, do a fourth root of 16 plus or minus 4. Okay, so there's a minus sign that you can't forget.
My leg is getting pulled. It's 2. 2 to the power of 4 equals 16. Yeah,
what's wrong? Sorry, slow down.
The answer is 2, not 4. 4 to the power of 4 is like a big...
Oh, fourth root, thank you. I did the plus or minus, but didn't do the fourth root. 2, thank you. So, that's how easy it is. It is really easy. So now you need to find them as points. Find them as points, which means I need to find the y values. So subbing, and you're going to need to do this, sub 2 in to where? The first equation back here. Okay, so type it in for me. -1 for the first one? Alright, so let's write when x equals 2, what did you get? Y equals -1? 140. And when x is equal to a -2, y equals 160? 116. Why can't I can't hear you properly. 116. Okay, so I have 2 stationary points. Let's actually write them as points. So 2, minus 140, and the other one is -2, 116. Okay, so now one more. Question 5. Show that y equals 1 over x is always decreasing for values of x in its domain. Okay, you might know that if I know what the curve looks like, but we have to show it. Okay, so we need to find the gradient, which means we need to differentiate it. You cannot differentiate an equation when the x is on the bottom, so the first thing I'm going to do is change that to be x to the power of -1. Okay, bring the x up. Now I can differentiate, so y dash equals, bring the -1 down the front, x, subtract 1 from the power makes -2. That is the derivative. Normally, best practice is to put that back into the same form as the question, so I would write that as -1 over x squared. Now, because we've done lots of work with graphs lately, you know that the denominator tells me something about the domain of that there? Yeah, well, no, back to here. X on the bottom means that X cannot be equal to 0. Okay, so there's one value that I know is I don't really have to check. The domain of my curve, X cannot be equal to 0. However, my gradient, what is happening with my gradient? No matter what X value I substitute into here on my denominator, positive or negative, if I put a negative number in here, I'm going to square it, and that denominator is always going to be positive. Okay? So the 1 over x squared part is always positive, but because I have a minus sign at the front, that means overall my gradient will always be negative. Okay? Which is the definition of decreasing and monotonic decreasing, because absolutely everything will always be decreasing. So let's write that out as a little explanation. So for all values of x in the domain, okay, so I've mentioned the domain because if 0 was on the bottom, obviously it can't work, because I can't have 0 on my denominator, but I already know 0 is not a possibility anyway. So for all values that are in the domain, x squared is positive. Therefore, the derivative, which means the gradient, is always negative. Hence, the curve is always decreasing. Okay, so that is showing it with our calculus, with doing our derivative. As I said before, you may have already kind of known that if you knew what that graph looked like. I'm kind of finished the question, but I just want to explain what this is visually. That graph, 1 over x, is a hyperbola. Okay? It has a vertical asymptote at 0, which is why our domain, we couldn't have x equals 0. It also has a horizontal asymptote here, also at 0, because I haven't moved it. And it looks like that. That's my basic hyperbola graph. Now let's have a look. If I start here, my curve is decreasing. Then my graph breaks. I start up here again, and my curve is always decreasing. Okay, so both parts of that curve are always decreasing, which is what I was proving with my calculus. All right, that's it. So I want to get used to the idea of differentiating to find stationary points and finding where it's increasing and decreasing. And we're going to be building on this every lesson.